So this is part A of that question, and take them piece by piece. This is actually, um, I think, a pretty good question for the modern AP exam to get look at because it's a experimental design graph interpretation type thing. Um, so uh, I'm assuming you've read this problem and you have questions on it. You're not just tuning in, so I try not to read every word for you. But they got a group of students have two carts. One A is going to be moving towards B, who's stationary. We're not worried about friction. Carts can travel along a straight horizontal track. They know the mass of cart A. The students are asked to use a one-dimensional collision between the carts. In other words, a collision hitting just like this, not hitting and going off at an angle. Um, Between the carts to determine the mass of cart B. Before the collision, cart A travels, like we said, and B is initially at rest, as shown above. After the collision, the carts stick together, so we have a completely inelastic collision. And they want us to describe the experiment to determine the velocities of the cart before and after the collision, including all of the additional equipment you would need. You may include a label diagram of your setup to help in your description. Indicate what measurements you would take and how you would take them, including enough detail so that another student could carry out your procedure. All right. So for the typical equipment, like the kind that we have in our room, it would look like this. So we would have a track that the carts would ride on. At one end of the track, I would set up a motion sensor. They're the little ultrasonic deals that send out ultrasonic pulses to measure the position, and then they can also give us velocities. So, motion detector. All right, and another one down at the other end. So assuming that the setup is like we see up here, we'd give cart A a push and start the data collection. So we'd get it moving and then start the data collection. So A would be moving. This would be recording A's velocity because it would be bouncing signals off the back of A. Meanwhile, B, which would be, say, sitting right here with its unknown mass, this would be reading its velocity. Now, which should be nothing. They could also, now that when I say reading the velocity, it could read position versus time, and you could find the slope. Or these things, ours will just read the velocity, period. So it'll tell you the velocity, which should be fairly constant here. They are connected. So the motion detectors are connected to, in our case, it's called a lab quest, but you could call it just simply a computer or an interface. You would read, so you basically say, and from those, you don't have to get too much detail, but from motion detector A, I would get a graph of the velocity from A, of cart A. And from this one, you would say you would get read another graph on here that would be the graph of the velocity of cart B. Also, you should have in here that once they collide and stick and start moving this way, both of them should be reading the same velocity. Of course, one would call it probably positive, the other would call it negative, but both would be, once they stick together, they would both be reading because they'd be moving at the same velocity. But this would get the initial velocity of B and the initial velocity of A. You technically, I guess you don't have to have this one. You could do this one and just assume that B is stationary, but it's up to you. If you did both, I don't think that would be the end of the world. Other than that, you don't really need the distances here or anything like that. These, a simple statement about we would use motion detectors to measure the velocities of each cart and, put them front and back of the cart. And like you said, you could probably just get away with this one. It's really all you need to say. So you'd add some words in here about the exact setup. And and just say, that the lab quest or the computer would give me the readout of the velocity or the position as a function of time. And either one would get you the velocity. So even if the graph gave you position as a function of time, that position would change for cart A, and the slope of that, of course, would be the velocity of cart A. In fact, we're going to see a little bit of that in a minute. So there's a rough setup. B. B is interesting. There will be sources of error in the measurements taken in the experiment, both before and after the collision. For your experimental procedure, will the uncertainty in the calculated value of the mass of cart B be affected more by the error in the measurements taken before the collision or by those taken after the collision? Or will it be equally affected by both sets of measurements? Justify your answer. Strange question. And I haven't looked at the answers, but here's my take on what they're pointing out. Uncertainty has a larger effect on small measurements. So in other words, if you are, well, here's an example that we've done in class. If you have a pendulum that you need to measure the period of, well, if the period is 1 second and your uncertainty is, your reaction time is 0.15, that means that's 85 to 15%, right? You've lost. You're 15% unsure on that in that case, or you're only 85% sure, however you want to look at it. So your error in that case would be as much as 15%. But if we measure 10 repetitions, so we get about around 10 seconds is what we measure, our reaction time can only affect the beginning and the end, so it's still going to be, say, 0.15. Now your error is down to less than 2%. It's 0.015 when you divide it by 10, so you get even less. So the longer the measurement, the bigger the measurement, the less it's affected percentage-wise by the error. So my take on it is it would probably be affected more afterwards, because I would expect the A's velocity will be pretty large. After they collide, that velocity will be less. This is a smaller measurement. If there's uncertainty, it'll be a bigger percentage of this measurement. That would be my take on it. I'm curious when we look at the answers to see if I'm even remotely on the right track with what they were expecting. But the overriding principle here is, if you're going to have uncertainty, it's going to increase the error more by percentage, looking at it as a percentage, when a value is small. So there you go. That would be my take on that. All right, let me get to what I think is the kind of the meat of the problem here. C. So they have a group of students who took measurements for one collision. A graph of the students' data is shown below. This is a position versus time graph. They identify cart A, and it's a little hard to see, but they identify cart B as these solid dots. Now, it would make sense that cart B would have no velocity, would have no change in position, therefore no velocity. This must be where the collision occurs. Okay, so from the information on this graph, and they finally give you the mass of A, they want you to calculate the mass of cart B. Okay, so forgetting right now what the graph can tell us. This is a momentum collision problem. That means the momentum initially has to equal the momentum final. And in the beginning, there's only the momentum of cart A. It's the only one that's moving. So I would write mass of cart A, velocity of cart A initially. There is no momentum for B, so that's all the momentum is here. After the collision, there's one object, but its mass is mass A plus mass B. Why? Because they stuck together. And they have a new final velocity. I'm just going to call V final. All right, so I've set this up. They've given me this. This is what they want me to find. I know A, of course. I need to see if I can get both of these velocities from this graph. Now, we just mentioned position versus time. If you're taking this year's AP exam, you should have a little cheat sheet that shows you what all the important things are for a position versus time graph, and there really is only one. The slope is your speed. So you need to estimate your slope here. Now, I don't know, you'd have a ruler if you were doing it in this year's. I don't know. So you take this. I'd do a best fit line as best I could here. Something like this. That's not too bad. That's the velocity of A before the collision, and then here they collide, and now I got a best fit line that's more like, let's see, 3 above, maybe like this, maybe a little more like this. It's not bad, maybe a little higher, but somewhere in there. So definitely two distinct velocities. All right, so I pick my best to find those velocities. So I look for places where the line that I drew crosses the axes, or at least close to it. Try not to use data points unless your line goes right through them. So I'm going to say maybe this point and this point. So here, I'll even use different colors. So in red, I chose, based on my line, I chose that, which looks black now anyway, but that's all right. Those 2 points, here and here. And I'm going to use my knowledge of mathematics to find the slope of the line between those. So let's see, that would be, let's do the change in y. So this one went from 0.5 to 1.1, it looks like. Yep. So the change in y is, we'll do 1.1 minus 0.5. Then the change in x is, let's see, it went from 0.3 to 0.7. So that would be 0.7 minus 0.3. And I would get a slope for this line, which would be my velocity, initial velocity, this guy here. So the initial velocity for A would be, I could probably do this, should do this on my own, that's all right. So it would be 1.1 minus 0.5 divided by, I can do that other one, 0.4, 1.5. So I get a velocity of about 1.5 meters per second. People are going to have different velocities in here. Don't, yours in mind, if you do it, they should be close. They don't have to be exact. If you show your work, like I did here, that you show that it's the slope and you calculate, then they're not going to argue with it. So I now know that I have mass of A, which is what, 0.5 kilograms, and the velocity, which is 1.5 meters per second. On the other side, in light blue, we got to find the slope of this messy line. I'm going to use, say, this point and this point. And we'll see how it goes. So this one is 2, 1.7. So this point here is the point 1.7 comma 2. And this point is 1.2 comma 1.6. Just pick 2 points off your line. Find their slope. So 1.7 comma 2. Let's see, and I started at 1.2 comma 1.6. So my change here in the y's is up 0.4. And my change in the x's was up 0.5. So the velocity, the final velocity of the two carts is going to be, change in y, which is going to be 0.4 divided by 0.5. 4/5 should be 2, 4, 6, 8, but let's just make sure. Yep, 0.8 meters per second. So I now know that I have MA, which is 0.5 kilograms, plus the unknown, MB, times 0.8 meters per second. So I'm pulling the velocities off of the slopes of these and using them in the momentum. And from here, it should be straightforward. We're just solving for MB over here. So we got 0.5 times 1.5. So I got 0.75 over here equals, let's distribute. So I got 0.8 times 0.5. So I got 0.4 plus 0.8 mass B. So I just distributed that. Now I'm going to solve for that. So I'm going to subtract 4 from both sides. 0.75 minus 0.4. 0.35 equals 0.8 MB divided by 0.8. And I get the mass of B to be about 0.438 kilograms. All right, so I got the mass of B to be about 0.438 kilograms. So once again, the slope of the position versus time is your velocities. This is the velocity of A before the collision. This is the velocity of the two of them after the collision. Use that in a proper, set up your conservation of momentum statement properly. You have just A is moving in the beginning, then the two of them combined are moving afterwards. All right, and that's how that's going to go. All right. D. The students are now asked to consider the kinetic energy changes in an inelastic collision, specifically whether the initial values of one of the physical quantities affect the fraction of the mechanical energy dissipated in the collision. How could you modify the experiment to investigate the question? Be sure to explicitly describe the calculations you would make, specifying all equations you would use, but do not actually do any algebra arithmetic. What? Okay, so here I think this is what they mean. Okay, so here, the confusing part. The initial values, whether the initial values of one of the physical quantities affect the fraction of the mechanical energy dissipated. So they're saying the only two things we have initially are either the mass of A or the initial velocity of A. And what they're saying is, set up an experiment where you vary one of these, do exactly what we did here, get the final velocities, right? And the initial. In fact, you would even just go ahead and you'd pick a mass for B and leave it. So in this case, you would just pick a whatever mass B you want and deal with it. And you could say, all right, we're going to vary the velocity. We're going to push it harder and harder and harder and harder. And we're going to see every time we do it, we're going to end up with a kinetic energy initial and a kinetic energy final. Of course, the initial kinetic energy is going to be 1/2 ma initial velocity of A squared. Your final kinetic energy is going to be 1/2 the two of them combined plus that final velocity squared. And you're going to compare those two kinetic energies, the initial and the final, and see what the difference is. And then change the velocity. Or you could change the initial mass, but I'll go with velocity. So, in other words, changing one of these initial conditions, to how does that affect the loss in energy? Is there a relationship between the two? So you would use the momentum equation that we used back there. Mostly just to find the velocity. Actually, you could use your data to find the velocity afterwards, your carts. So really, there wouldn't be many calculations here because you would be able to read this and this off of the carts. If the masses were consistently the same, if this is the thing you're changing, you're really looking at how this changes and therefore how this changes. But these would be the big equations right here. Because I would change this and see how this reacts. And then change it again and see what, and so forth and so on. So that'd be my take on it. And so to explicitly describe the calculations, I would find the kinetic energy of the initial using this, and the kinetic energy final using this. I would know the masses, and I would measure the velocities before and after. And that would give me all I would need to know. And I would vary this, say the velocity, keeping everything else constant. All right. D, is that all of them? I got A, B, C, D. I think that is it. All right.